have our next speaker, which is Adrian from ACSC. He's going to be speaking about Introduction to Cisco iOS Analysis. So thanks, Adrian.
Hope everyone did see the schedule changed and you're not all going to be very disappointed by this. So I'm going to be talking today about how to get started with analysing Cisco iOS both images and memory dumps in the hope of sort of lowering the entry bar and starting to find these newer forms of malware that are starting to come out. So my name is Adrian Justice. I've been an incident responder with the Australian Cyber Security Centre since 2015. And last year I got the opportunity to step away from doing normal IR work and start doing some research into how we could potentially do forensic analysis of these iOS devices. So why did we all of a sudden start doing this? Well, it was largely thought that routing malware was a theoretical thing. I mean, they're still computers, there's no reason why you couldn't have malicious code running on them, but they were just so damn complex and such a high entry bar to start developing this stuff. That changed in 2015 when Cisco and FireEye came out and announced that Sinful Knock had been found. So Sinful Knock was a full iOS image replacement, which essentially is the equivalent of replacing all of Windows just to get your malware onto the system. It works, it's effective. So this provided full backdoor functionality, admin access, all the sort of stuff you'd expect from essentially a rat. So seeing that this was now a thing, I figured it's only a matter of time before everyone starts to get more into this sort of malware development. I mean, if you can compromise a corporation's core router, you've got access to their everything. You can choose what web pages they can see, you can redirect web pages. It's good for an attacker, really shit for a defender. There's no malware for routers these days. So I'm going to be covering what iOS looks like both on disk and in memory, how to acquire memory from a device so you can continue analysis, a bit of how to mangle iOS images to make them sort of a bit more friendly to standard analysis tools, and we'll finally go through some current attack vectors. So just so everyone's up to the date, we're talking Cisco iOS, like the original one here, not the Apple imitation that came out years later. So first off, when I'm talking about an iOS image, I'm talking either the file you download from Cisco if you're an official sort of vendor licensee of them, or one you rip off your dodgy router you got secondhand on eBay to do all of this research on. This is the thing that is stored on the internal storage or CF card that is then extracted into memory to actually run. So the file that you download or acquire by various means is a fairly standard Linux ELF file looking thing. It won't run on normal Linux, but it still has the same structure. So you've got a normal ELF header, there's a small decompression program, a bit of validation information to verify both the checksum and the size of what you've acquired, and finally a compressed copy of iOS. This is just the normal structure of an ELF header. I'm not really going to spend time on this because it's ELF. No real difference for the iOS version. The one thing of interest is the machine ID field, which is typically used to confirm the processor type that this binary is being compiled for. For whatever reason, Cisco don't use the right value here. They use values for processor types that don't exist. So this can have some issues when you start trying to analyze this in normal tools, but we'll get more into that a bit later on. The compression header is a nice, useful one just for verifying sort of the integrity of what you've actually gotten. So if you search for the magic string of feed face, you've got the size both uncompressed and compressed of the data, the checksum of the compressed and uncompressed data, which can be calculated using that Python function up the top there, and finally the actual zip data, which is highlighted in blue down the bottom, although it didn't come out too well. It's a stock standard zip header, PK, blah blah blah. Towards the very end of the disk, there's this fade-fad couple numbers with an MD5 after it. I cannot work out what this is an MD5 of, and according to Cisco's website, it is a MD5 hash of some sections of the file. They don't bother to tell you which one, so you can actually verify this yourself. The only way you can verify it that I've found is to use the inbuilt iOS verify command, which is great because you have to verify the integrity of a compromised system on the compromised system. Yeah, so if anyone does know what this is, happy to find out. There's also these CW strings, which are kind of a bit of an informational sort of thing if you've just been given a random image to analyze. So these contain information such as the feature set on the device, like what the encryption it has, the firewall it has, whether it has IP, because that's optional on routers. The model number of the device, the version number that you're dealing with, and some various other things. They're all just strings sitting there, so they're nice and easy to extract. They've got the format down the bottom there in green. So we'll move on to what this looks like once it's in memory, because I mean, if you're dealing with a bit of malware these days, that's kind of where it's a bit more interesting. Just a bit of a full disclosure sort of thing here. This has been pieced together by reading like 16-year-old exploitation white papers and like reading through people's really poorly documented code. It's also, it should be noted that I'm talking about iOS here, not the newer iOS XDR blah 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 ranges, which tend to be running under a more Linuxy sort of system, which I haven't looked into this, but theoretically you can use sort of standard Linux memory forensic techniques against. So each block of process memory that's allocated has this struct wrapped around it, and there's a lot of stuff here, so I'm not going to go through it all, because quite frankly most of it's pretty boring. But I would not recommend putting the magic string of AB1234 CD into a hex editor, because there is hundreds of thousands of these things across a memory dump. Things of interest are the process ID, so you can use this to start to piece together all the individual sections of memory that are allocated to a specific process. But PIDs are kind of boring, like I want to see the names, so you can use the allocation name field, which is just a pointer to a section of memory that contains a null terminated string for that process. This whole structure is a doubly linked list, so you're also able to walk up and down every bit of process allocation and start to build your own tree up of sort of what the memory looks like. You've got the size of the data itself, and this red zone value at the end, which is best I can tell is sort of like sort of the equivalent of a stack cookie or that sort of thing. So if you go and overwrite your memory allocation, you overwrite this value, the next time the integrity checker comes through, it sees that and freaks out. When iOS freaks out, it kernel panics and the whole router reboots, which is kind of good from a defense point, because if someone screws up their exploit, then the router's gone. So my normal job is incident response, so if I can roll into a network and there's the full command history of what someone's done on the router, that's awesome. These things are ridiculously easy to extract out of memory. You can literally just run strings and grep for CMD and you'll get the full time code of the command that was run and everything. Unfortunately, this isn't persistent, so as soon as you log out of the device, it seems like the memory is freed. So it's not zeroed, so it does stick around for, say, a minute or two, depending on how heavily used the router is, but yeah, still please push this out to a syslog server if you have access to this stuff. So this is a rough example of what you can pull out of a device. So you're able to see, I was running like the show run command, I configured some exception dumping stuff, I typoed the copy run command, the router tried to connect to soppy run start for some reason, and finally actually managed to configure it properly. So you can also extract the device's configuration from memory. So a little bit off topic, but you can change, interfere with what gets output to the Cisco command line. There's like filters you can build into it to sort of use regex queries to determine what the user actually sees. So it is possible to write things into the config and then filter out them actually being printed back to the screen. So if you suspect someone's screwed with your config, it might be useful to extract it raw out of memory. It's sitting in memory in the same format that you would normally get from running the show run start command. So you can just show run command. So you can just search for the last configuration change string, and you'll see the entire config just sitting there in memory. So enough about what you can do with iOS memory. Like, how do we actually get a copy of it to start playing? So we're going to go through some of the more official ways, and since we've got a bit more of a technical group, I'll go through some of my more experimental ways that sort of theorizing but haven't had a chance to test out yet. So the official way is what's on Cisco's website. If you want to configure one of these, you configure the exception handler, you tell it to dump it out to a TFTP server, and you just run the right call command. Supports compression, relatively straightforward to do. If you're just wanting to start playing with this stuff, this is a pretty good way to start. It also is the official way, so anyone that's actually trying to do some form of anti-forensics with any malware is going to know about this command and is going to do something to screw with it or give you false results or just kernel panic the router and they're gone out of memory as well. So you can also copy individual segments of memory. So there's sort of like pseudo file pointers exposed to the individual regions of memory that you're able to use to copy out. It's another one that is relatively well known though, so don't be surprised if this is filtered out as well. So the worst kept secret of iOS is that for the last 15 years or whatever, it's had a GDB server built into it. So you can only access it through the front console port, which means you're now running everything over serial at the amazing speed of 9600 baud. Once you do this, you've got full read-write access to memory, so it is possible to dump the entire contents of memory. On my 2800 router that has 256 meg of RAM, it was going to take 2 or 3 days to dump memory. If you walk into an actual organisation where they've dropped like 500 grand on a decent half-rack sort of switch, and you say, I need to take that offline for a month while I do a dump over my serial cable, good luck with that. So yeah, pros, really good memory access, cons, really freaking slow. It's also been disabled in the newer versions of iOS, although it can be re-enabled through ROM1, which is kind of Cisco's equivalent of the BIOS. But doing that does require rebooting the router, so you lose anything that's potentially sitting in memory. It also does, lock the full router up while you're doing this, so yeah. So when you crack some of these older devices open, they're using fairly standard PC hardware, which is kind of nice because the same attacks can apply. So my old 2800 series router uses old DDR RAM. Theoretically, there's no protection against a cold boot attack. The big protection is it's really freaking hard to find an old Pentium 4 that you can chuck their stuff into to test it on. But we have a lot of IT people around, and thankfully I have managed to track some down. I'm still waiting to actually receive them though, so I can play around with this. Another one that good luck convincing someone to let them do this as far as like an active investigation, because you're cracking open their running router, spraying freeze spray into it, and then yanking the RAM out while it's still running. Minor risks there. You also have to be careful that the hardware you're putting this into doesn't support ECC, because all this RAM does, and zeroing the RAM that you think has stuff in it when you boot it up is not a good thing. Go to the other side. If you exploit these routers, they're sitting there running everything as a single process, so any running process on it has direct memory access. We're starting to see more and more CVEs coming out for routers and switches, and quite a few of these are for devices that are never going to be patched. Again, my 2800 was end-of-lifed in 2016, and there's still flaws coming out for it. Like, there's a recent one for like the SNMP server and stuff like that. So given a sufficient amount of effort, you could easily write your own sort of mini router implant that can dump memory out over the network. There's the slight issue that all of these devices have quite a broad range of hardware that they run on. So you sit there and write your shellcode to do a memory dump for the PowerPC model, then you've got 1,000 different MIPS models and stuff like that. So not really a scalable solution, more of a, if someone wants to get a PhD out there and write this, then that'd be sweet. So you aren't left fully unprotected on these devices. There are a decent number of protections, but there are a decent number of bypasses for the protections as well. So there is depth built into these routers. So the stack of the router, as well as like the I/O memory where your packets are stored, is protected. So I can't send a packet that has executable shellcode in it and just jump to it. Unfortunately, it is quite bypassable, so there's well-known ROC gadgets out there, so if you can gain some form of code execution, you can disable depth and you're back to square one. There's also code integrity checking that does a basic checksum over the various segments of the code memory to make sure that you haven't like overridden any of it. It is a fairly basic checksum though, so it's theoretically possible just to brute force your shellcode so that it now matches a new checksum, or you just bypass depth and don't overwrite the code section. Watchdog time is not really intended as a security mechanism. It's more of a stuff broke and we don't want to like take the router down. So any process on the router that doesn't return control back to iOS periodically will be killed by the watchdog timer. It just means if you screw up your shellcode and don't return back to the controller, then your shellcode gets killed as well. But again, there's fairly well-known ways around this, like just hold the sleep function. It's fairly straightforward. There is actual ASLR, but only on newer routers with newer updates, so my poor 2800 is going to be vulnerable forever. And there's a thing that I found in an old DEF CON talk by FX about the fake ASLR. So every version of iOS that's compiled for every individual device, subversion, hardware configuration is an individual compilation, which means as these are a giant statically linked binary, everything's laid out in memory from like different offsets every time. That means there's about, well, back in 2009, there was 300,000 different iOS images out there. It's probably a few more in the last 10 years of people doing this. That's well over 300,000 different memory layouts. So it actually provides better protection than actual ASLR. So the odds of you being able to write something on your router using a fixed offset that you jump to, and then throwing that against my router, pretty decent odds you're just going to crash my router, not actually gain control. So iOS is a bit weird, and I don't know if Cisco is trying to stop you analyzing it, or if this is just like parts of the image that they don't use because like they have full control of the system, so they don't need to worry about it. But yeah, it looks a bit funky and does make some tools freak out. So first up, if you want to analyze this stuff, you've got to actually extract it. As I mentioned before, it is just a stock standard zip file at the end of it, so thankfully the Linux unzip command can spit out, it'll strip off all the elf header crap at the start and just spit out a nice image for you to analyze. So if you do want to start poking around inside, IDA is probably what you're going to want to load this into. This is where we come back to that machine ID field I mentioned in the elf header that's wrong. So when you load this into IDA, it's going to read it, see it's an elf header, jump to the machine ID field to work out what sort of instruction set to use to disassemble this, and freak out because it's got no clue what it's doing. So you can go and research what this device actually uses and go and patch the file, and yeah, everything will be good to go. It's a lot of effort. You can learn how to use IDA properly and just select the drop-down menu and say this is designed for PowerPC. I didn't see that drop-down menu the first time. So when you do it the convoluted way, here's what you can get. So running EXIF tool over the original one, you can see the bottom field, it's got CPU type of unknown. After patching it, it's now PowerPC, and IDA happily sees it. So IDA's all well and good, but it's not every tool you want to use for this. So there's other random stuff that tends to freak out as well. I've had hex editors that try to auto walk the elf header in this that end up in infinite loops because they don't understand what big endian is and things like that. So while endianness is not an iOS specific problem, I'm analyzing anything that's not x86 and little endian. There's a lot of tools that just assume that you're analyzing an x86 binary. And while they will work with a little bit of tweaking, it's not nice. So the best I've come up with, short of rewriting the tools to actually obey the endianness flag in the elf header, is to read all of the values out, flip the endianness, and write the elf header back. Obviously this breaks the binary, but at least you can analyze it properly then. The section header is quite a useful one, so it details all of the different permissions and names of the sections within the file that you're analyzing. Again, for whatever reason, Cisco didn't label one of the regions right, and the region they didn't label right is the offset to the string table that contains the names of all of the sections. It's a bit intensive to fix this one. You need to go and track down the correct string table using that, well, if we had screens, you'd be able to see the thing, there we go. We have no mouse. That STR tab value down the bottom there. Once you find that, you have to manually parse the section header or section table yourself and find which entry points to that. And finally, you can patch the type of that thing to say this is actually a string table, which goes from the value that's on the left where everything is just no name to on the right where you can see here's the text section, blah, blah, blah. The very bottom there, number 12, is the actual string table. You can see it's now got a value of STR tab rather than no bits on the left. So that's all stuff we can do to find actual malware, but so what's actually happening out there on the internet? It's all just basic stuff like abusing things that are baked into these devices. So 12 months ago, the big thing was SNMP config exfiltration. So this is just you brute force the right community string in these devices, use that to reconfigure the TFTP server of the device. And finally, by SNMP, you say, hey, you're currently running config out to the TFTP server, because that's a thing you can do over TFTP. Fairly straightforward to fix this up. Like SNMP is just using essentially passwords. Like a community string is a password, but it's a password you only have to type in once to a device. To make this thing really freaking strong, and no one's going to be brute forcing it over the internet. Also, if you don't need write access to the internet, don't expose write access to the internet. This feels basic, but it still happens. As an added bonus, you can also overwrite the current configuration, the current running image of the device using this. So if someone's out there doing sinful knock type stuff again, they can overwrite or they can drop sinful knock on your device using this. So the newest thing is Cisco Smart Install. So I think it's late last year at one of the Russian security conferences, they sort of dropped that you can use Cisco Smart Install to exfiltrate device configurations as well. So again, it's not a bug, it's a feature. This thing supports zero-touch configuration. Part of zero-touch is you can't type in correct, so there's no authentication built into this thing either by default. It's intended so that you can just post a switch off to the other side of the world, hook it up to some form of IP connection, and you can send it a config and an image. This guy worked out that, well, part of zero authentication is it doesn't know who's requesting this, so he wrote his own, Cisco call him a director. So he wrote his own director that can both send it a new configuration as well as tell it to send it back its current configuration. So that's up on GitHub if you want to play with it. Please don't target Australian routers, I don't want to have to clean it up. So to turn it off, well, to fix it, turn it off. Cisco's apparent thing of it's on by default because people use it. Not enough people use it, please turn it off. So that was originally going to be the end of this presentation, and then last Saturday someone did this. So someone did work out that that same GitHub tool can go in the other direction and overwrite the current configuration of the device. Again, no authentication. They use that to go and wipe out all of the switches in Iran and replace it with a "don't mess with our elections" and this lovely ASCII art US flag. So you'll see in the screenshot there, this is just someone's putty section. They're actually running the show start config command. Normally this would show actual iOS commands to configure the device, but they've just replaced the whole thing with a text file because there's also no validation of the configuration file you write to this thing. So this thing literally just boots up saying, well, shit, there's no config, and just it tries to actually execute each line of the ASCII art flag, which is quite fun when you do this. But then it freaks out, loads of default config, and all of a sudden Iran's knocked off the internet for a while. Also saw one report, or I think it was on Motherboard, saying that they also targeted both the US and the UK, but in that one they just went and turned off Smart Install on all of the devices, so they're sort of calling them vigilante hackers now as well. So yeah, really easy to do, script kiddie level of stuff. As I said, this is on GitHub, it's literally point and click and bye-bye router. So please turn this off if you've got it. That's about it. If this is sort of interesting to you, then the careers page is up there. Come and join us. You too can come and do presentations here.